December 8, 1941. Fort Monmouth, New Jersey. Major General James O'Connell stood in the Signal Corps laboratory, holding a field radio that weighed 47 pounds and had a reliable range of less than 3 miles. Behind him, 26 identical units sat in wooden crates, the entire tactical radio inventory available to deploy with the 31 Army divisions that would soon be fighting a war on 2 continents. He set the radio down and asked his chief engineer a question that had no good answer. How do we communicate across a battlefield when we don't have the radios to do it? The attack on Pearl Harbor had brought America into the war with stunning force. But in the months that followed, military planners discovered something almost as alarming as the Japanese offensive capability. The United States Army possessed fewer than 800 portable tactical radios suitable for field use. The Marine Corps had even fewer. The Navy's ship-to-ship communications were adequate, but ground forces, the men who would fight in North Africa, Italy, France, and across the Pacific, had almost no means of coordinating movement, calling for artillery support, or requesting medical evacuation under combat conditions. In a war that would be defined by combined arms operations and rapid mechanized movement, American forces were preparing to fight in near silence. This is the documented story of how American engineers, denied the luxury of time and working without established military specifications, built a combat radio network from the only components available to them, the mass-produced parts of the American automobile industry. The radio shortage of 1941 was not the result of oversight. It was the consequence of 2 decades of deliberate choice. After the First World War, Congress had reduced military communications funding by 73%. The Signal Corps, responsible for all Army communications, saw its research budget fall from $4.2 million in 1919 to $600,000 by 1933. Commercial radio was booming. American homes had more than 30 million receivers by 1940, but military radio development had effectively stopped. What portable military radios did exist were built one at a time by hand. The SCR-194 and SCR-195, the standard infantry radios in 1941, were constructed using components designed for stationary laboratory use. They employed large glass vacuum tubes that shattered under field conditions, required separate battery packs weighing 18 pounds, and needed 7 minutes to set up before transmission. The operating range under ideal conditions was 5 miles. Under actual combat conditions, with terrain, weather, and electromagnetic interference, effective range dropped to less than 2 miles. In desert conditions, where heat affected battery performance, some units reported ranges of under 1 mile. The Marine Corps 1st Division, preparing for deployment to the Pacific in early 1942, had 11 SCR-194 radios for an entire division of 19,000 men. The Army's 1st Armored Division, training at Fort Knox, had 37 radios to coordinate 247 tanks, 78 half-tracks, and 54 self-propelled guns across a mechanized battlefield. Artillery forward observers, men whose entire function was to radio target coordinates to gun batteries miles behind the lines, often had no radios at all. They were issued signal flags and message runners. By January 1942, the War Department had calculated the requirement. To equip the 89 divisions planned for deployment by 1944, the Army needed 130,000 portable radios of various types. To support amphibious operations across the Pacific, the Marines needed another 18,000. The Navy required 22,000 additional units for landing craft, shore parties, and ship-to-shore coordination. The total requirement was 170,000 military radios, and production capacity in January 1942 stood at 1,100 units per month, all of them still being built by hand using components that were already in short supply. The Signal Corps Engineering Laboratory at Fort Monmouth faced a problem that transcended normal procurement. They could not simply order more of the existing radios. The vacuum tubes used in the SCR-194 were manufactured by Western Electric using equipment that produced 700 tubes per month. Scaling up production would require building new factories, training new workers, and developing new supply chains for specialized materials, a process that would take 18 to 24 months. The Army would be fighting with signal flags until 1944. The solution came from an unlikely source. In February 1942, a civilian engineer named Paul Galvin met with Signal Corps officers in Washington. Galvin owned a company in Chicago called Motorola, which manufactured car radios for Chevrolet, Ford, and Chrysler. His factories had the capacity to produce 8,000 radios per month, and had stockpiles of components designed to survive automotive environments: temperature extremes, vibration, moisture, and shock. He asked the Signal Corps a direct question. Instead of building military radios from scratch, what if we adapted car radio components for military use? The proposal violated every principle of military procurement. Car radios were designed for entertainment, not tactical communication. They operated on different frequencies, used different power systems, and had none of the durability features required for combat equipment. Military specifications called for equipment that could function after a 6-foot drop, survive immersion in salt water, and operate in temperatures from -40 to +130 degrees Fahrenheit. Car radios were built to survive a drive to the grocery store. But the Signal Corps had no alternative. On March 3, 1942, Colonel William Baer authorized Motorola to begin prototype development. He gave them 6 weeks. The engineering challenge was substantial. Military radios needed to operate in the frequency range of 20 to 52 megahertz for tactical communications. Car radios operated at 540 to 1600 kilohertz in the AM broadcast band. The frequency difference alone required completely different tuning components, different antenna designs, and different power amplification. Military radios needed frequency stability within 0.01% to prevent signal drift during extended operations. Car radios drifted freely, a minor inconvenience when tuning to a music station, but fatal to coordinated military communications. Galvin assigned a redesign to his chief engineer, Dan Noble, who had joined Motorola from the physics faculty at the University of Connecticut. Noble understood that he couldn't simply modify car radio circuits. He had to rebuild the entire signal chain using components that were available in automotive industry quantities. He started with the tubes. Car radios use small vacuum tubes designed for 12-volt automotive electrical systems. They were far less fragile than laboratory tubes because they had to survive engine vibration and the shock of potholes. They were also manufactured by the millions. RCA alone was producing 200,000 automotive tubes per week for civilian market. Noble selected a tube designated the 6K7, used in Ford radios, as the basis of the radio frequency amplifier. For the power output stage, he chose the 6V6, a tube Chevrolet used in higher-end models. Both tubes were rated for mobile use and were already proven in harsh environments. The power supply presented a different problem. Military radios needed to operate independently, often for days, in locations without any external power. The existing SCR 194 used 3 separate battery packs, one for 2 filaments, one for plate voltage, and one for bias voltage. The combined weight was 18 pounds, and battery life under continuous operation was 4 hours. Noble eliminated 2 of the 3 battery systems by redesigning the circuit to run entirely on a single 12-volt supply, identical to a car battery. This reduced battery weight to 6 pounds and extended operating life to 11 hours. Frequency stability required precision components. In laboratory radios, this meant variable capacitors with ceramic or mica insulators, hand-adjusted to maintain calibration. These components cost $12 each and required skilled technicians to install and align. Noble replaced them with stamped metal capacitors using automotive-grade materials, costing 41 cents each. They were less precise, but by using 3 capacitors in series instead of 1, he achieved the required stability at 1/10 the cost and with components that could be installed by assembly line workers. The antenna system was perhaps the most visible adaptation. Military radios traditionally used whip antennas, spring steel rods that extended 8 to 10 feet above the radio. They were effective but conspicuous, marking radio operators as high-value targets. Car radios use much shorter antennas, optimized for AM broadcast reception. Noble couldn't use broadcast antennas for military frequencies, so he designed a telescoping antenna using the same spring steel material that Buick used in sedan antennas. It extended to 74 inches for transmission and collapsed to 12 inches for storage. More importantly, it could be manufactured using existing automotive tooling at a rate of 15,000 per week. By April 15, 1942, Noble had built 3 prototype radios using entirely automotive-sourced components. Each unit weighed 17 pounds, operated for 11 hours on a single battery, and had a demonstrated range of 7 miles under field conditions. The Signal Corps tested them at Fort Monmouth over a 2-week period, subjecting them to the standard durability protocol. Repeated drops from 6 feet onto concrete, immersion in salt water for 30 minutes, operation at minus 20 degrees for 4 hours, and operation at plus 120 degrees for 4 hours. 2 of the 3 prototypes functioned normally after testing. The third required replacement of a single tube. On May 1, 1942, the Signal Corps issued a production contract. Motorola would build 12,000 radios, designated the SCR 300, with deliveries beginning in July. The contract specified that at least 70% of all components must be sourced from automotive suppliers. Production began on June 8th at Motorola's plant on Augusta Boulevard in Chicago. The facility had built car radios for 5 years, and the assembly process for the SCR 300 followed automotive industry practices. Workers installed components on a moving assembly line, with each station performing a specific task. Tube insertion took 8 seconds. Capacitor installation took 12 seconds. Wiring harness attachment took 26 seconds. The entire assembly process, from bare chassis to completed radio, took 14 minutes. By the end of June, daily production reached 73 units. By August, it reached 190 units per day. The automotive supply chain made this possible. Vacuum tubes came from RCA's plant in Harrison, New Jersey, which was already producing 50,000 automotive tubes per day for civilian car radios. Capacitors came from Aerovox, which supplied ignition capacitors for General Motors. Resistors came from International Resistance Company, which made voltage regulators for Ford. Transformers came from Thordarson, which built ignition coils for Chrysler. None of these suppliers needed to build new factories or develop new processes. They simply redirected a portion of existing automotive production to military contracts. The cost savings were extraordinary. The hand-built SCR 194 radio, purchased in small quantities before the war, cost the Army $137 per unit. The automotive-based SCR 300, built on assembly lines using mass-produced components, cost $53 per unit. Even accounting for the development costs and initial tooling expenses, the Signal Corps calculated that the automotive approach saved the Army $41 million on the initial order of 12,000 radios. But cost was secondary. What mattered was volume. By December 1942, Motorola was producing 400 SCR 300 radios per day. Galvin had licensed the design to 5 other manufacturers: RCA, Philco, General Electric, Stromberg Carlson, and DeWalt Radio, who added their own production capacity. By March 1943, combined production across all 6 manufacturers reached 1,800 units per day. By the end of 1943, the Automotive Radio Network had delivered 96,000 portable military radios to American forces worldwide. The SCR 300 arrived in combat with the 1st Infantry Division during Operation Torch, the invasion of North Africa, in November 1942. Battalion commanders used them to coordinate movement across the Tunisian desert, where distances between units often exceeded 10 miles. Forward observers used them to direct naval gunfire from ships offshore onto German positions inland. Tank platoons use them to maintain formation during rapid advances, eliminating the need for visual signals that enemy forces could observe. The operational impact was immediate. In North Africa, American artillery response time, the interval between a forward observer identifying a target and shells landing on that target, dropped from 23 minutes using runner-delivered messages to 4 minutes using radio communication. Tank companies maintain coherent formation at speeds exceeding 15 miles per hour, where previously they had fragmented into isolated groups moving at walking pace. Infantry battalions coordinated flanking maneuvers across terrain where visual contact was impossible, executing combined arms attacks that had been theoretical exercises during training. In the European theater, the SCR-300 became standard equipment for airborne operations. Paratroopers carried them during the Sicily invasion in July 1943 and the Normandy invasion in June 1944. The radios allowed scattered units to locate each other after night drops, coordinate assembly areas, and call for resupply. During the Battle of the Bulge in December 1944, surrounded American units used SCR-300 radios to direct supply drops and coordinate defensive positions while completely cut off from ground contact. The automotive component strategy extended beyond portable radios. In 1943, the Signal Corps contracted with Bendix Aviation to develop a vehicle-mounted radio using the same principle, automotive components adapted for military frequencies. The result was the SCR-508, which used a 12-volt electrical system identical to military trucks, featured push-button channel selection like a car radio, and could be installed in a Jeep or half-track in under 2 hours using standard automotive tools. Bendix produced 47,000 SCR-508 radios between 1943 and 1945, creating a mobile communications network that extended from divisional headquarters to individual tank platoons. By 1944, the automotive radio program had expanded to include replacement parts. The Signal Corps established depot-level repair facilities in England, North Africa, and Australia stocked with automotive standard components, tubes, capacitors, resistors, and transformers that field technicians could install without specialized training. A damaged radio that would have required factory return and a 6-week repair cycle under the old system could be repaired in the field in under 4 hours using components that supply sergeants order from the same catalogs they use for vehicle parts. The production numbers tell the full scope. Between June 1942 and August 1945, American manufacturers produced 183,000 SCR-300 portable radios, 74,000 SCR-508 vehicle radios, and 91,000 SCR-536 handheld radios. A smaller, shorter-range design also based on automotive components. This represented a 640-fold increase in tactical radio availability compared to December 1941. The automotive component strategy had not only solved the immediate shortage, but had created a communications infrastructure that exceeded the original War Department requirement by 37%. The engineering approach pioneered by Motorola became the template for wartime electronics production across multiple systems. In 1943, General Electric adapted automotive voltage regulators for use in radar systems, reducing production time from 4 weeks to 6 days per unit. In 1944, Raytheon adapted automotive ignition components for proximity fuse production, increasing output from 8,000 to 93,000 fuses per month. The principle was consistent. Wherever possible, use components designed for mass production in harsh environments rather than custom-built components designed for laboratory precision. The cost implications extended beyond immediate procurement savings. By using automotive components, the military created a supply chain that remained functional under stress. When German U-boats sank shipping in the Atlantic, replacement parts for automotive-based radios could be sourced from domestic suppliers with weeks of inventory. When bombing disrupted factories in Europe, automotive suppliers had multiple facilities capable of producing identical components. The robustness of the automotive supply chain, built to serve millions of civilian vehicles, proved more resilient than specialized military supply chains built to serve thousands of units. there were limitations. The automotive-based radios were less precise than laboratory-built equipment. They drifted slightly in frequency, requiring periodic retuning. They were more susceptible to interference from electrical storms and atmospheric conditions. They had shorter maximum range than theoretically possible, with optimized designs. But these limitations were acceptable because the radios existed in sufficient quantity to compensate. If interference affected one frequency, operators switched to another. If range was insufficient, units positioned relay stations. The tactical flexibility provided by widespread radio availability outweighed the technical limitations of any individual unit. After the war, the automotive component approach remained standard. The N/PRC 25 radio, which became the primary infantry radio during the Vietnam War, used components derived from automotive electrical systems. The N/PRC 77, which replaced in the 1970s, continued the same design philosophy. The Sinkers radio system, introduced in the 1980s and still in use today, employs frequency hopping technology, but its power supply, environmental sealing, and mechanical design all trace directly to automotive engineering practices established during World War II. The engineers who built radios from car parts were solving an immediate crisis, but they established principles that shaped military communications for 80 years. They demonstrated that mass production, even with compromises in individual unit performance, could deliver capabilities that custom manufacturing could not match. They proved that automotive industry practices, standardized components, assembly line production, distributed supply chains, could support military requirements when adapted thoughtfully. They showed that the speed of deployment often mattered more than perfection of design. Major General O'Connell retired in 1946. In his final report to the Signal Corps, he wrote that the radio situation in December 1941 represented the most dangerous communications gap in Army history, and that the automotive component program had closed that gap in less than 18 months. He noted that without that program, coordinated operations in North Africa, Italy, and France would have been impossible at the speed required, and that Pacific Island campaigns would have suffered substantially higher casualties due to inability to coordinate fire support. Dan Noble remained with Motorola after the war, eventually becoming chief scientist and leading the development of commercial mobile radio systems that evolved into cellular networks. Paul Galvin continued running Motorola until his death in 1959, but he rarely discussed a wartime radio program, considering it simply a matter of applying available tools to an obvious problem. The SCR 300 radios themselves remain in service through the Korean War. Many units deployed to Korea in 1950 carried SCR 300s manufactured in 1943 and 1944, still functioning with original components. Some remained in National Guard service into the early 1960s. A small number are still maintained in working condition by military museums. On a shelf in the Fort Monmouth Museum, an SCR 300 radio sits in a display case next to a 1942 Chevrolet car radio. The internal components, tubes, capacitors, transformers, are nearly identical. The difference is in how they were arranged, what frequencies they covered, and what purpose they served. One brought music to American families driving to church on Sunday mornings. The other brought coordinated fire support to American soldiers fighting in hedgerows, jungles, and deserts 7,000 miles from home. Both were built on the same assembly lines by the same workers, using the same tools. That shared foundation, improvised during a moment of national emergency, proved sufficient to win a world war and establish the communications architecture that still connect American forces in the field today.